Now we've learned the things that we need to know in order to understand the Wolff-Kishner reaction and its mechanism. So first, the general reaction. The general reaction is that we take a carbonyl compound and we react that with hydrazine, potassium hydroxide. This is concentrated, 6 molar, and we heat this up. And again, in simplistic terms, we convert that aldehyde or ketone, mostly it's used for ketones, could be done with aldehydes, to a CH2 group. Now, hydrazine. Anybody recall what hydrazine is? It's rocket fuel. The Saturn V rocket that powered folks up to the moon burned hydrazine. So it's a high energy molecule. You don't want to play around with it in a risky fashion, but again, we're at risks every day. We manage those risks. So let's look at a specific example here. Again, just something simple so that we get the idea. If we had a carbonyl group here, we know how to do reduction of a benzylic carbonyl to a CH2. Do you recall that? That was palladium on carbon and hydrogen. But of course, with palladium on carbon and hydrogen, we would also reduce the nitro group. But because of the mechanism of this reaction, and this is what I call a mechanism-based reduction, it's not electrochemistry, it's not electron transfer, it's not hydrogen addition, so there's some other mechanism going on, then we can actually accomplish this reduction. So again, hydrazine, 6 molar KOH, and heat, and these are heated up pretty good, typically about 100 degrees or so. You can reduce this. You don't touch the nitro group, and you reduce the carbonyl to a CO. So this is a very useful reduction to give us selectivity, and that's the way we'll use it in our class, is to make use of it in selective reduction for multi-step synthesis. Now, how is it that this occurs? Well, it turns out that the reactions in the chemistry that we've been learning are very critical to this. First, hydrazine. Let's look at this structure in a little more detail. Is an example So hydrazine is an example of what we call the alpha effect. When the atom next to the one of interest has a lone pair also, that is the alpha atom, then the nucleophilicity of that lone pair of atoms is greatly enhanced. And so you don't need base or acid catalysts. Now, obviously, we have basic conditions under the Wolff-Kishner. But with hydrazines, another example of this being hydroxylamine, or substituted hydrazines. One that you might use in the lab is the paranitrophenylhydrazine. These will react very rapidly with carbonyls to make the equivalent. They're not exactly imines, but they're close. Obviously, they don't have alkyl substituents the way the imines do. So for instance, if we take this paranitrophenylhydrazine and we react it with a ketone compound, this is what we call, in fact, in the undergraduate laboratory, this is often a qualitative test for carbonyl compounds. It can be an aldehyde, could be a ketone. These spontaneously react, and in seconds to minutes can precipitate colored solids. So this aromatic nitro group conjugated through all these, remember there's a lone pair here, and another lone pair here, conjugated through this system, often give colored materials, and these precipitate. Now, this was a hydrazine, this is a hydrazone, and the equivalent made with hydroxylamine is called an oxime. Now, I'm not going to get into more details about those in this discussion, but you want to recognize those as examples where we have this alpha effect. You have an alpha atom with a lone pair, so this nitrogen is much more reactive and that nitrogen is much more reactive. Now, let's look at the mechanism of the Wolff-Kishner. I think I can squeeze it on the screen here. So, the carbonyl compound is an electrophile. The hydrazine is a good nucleophile. We get nucleophilic attack, and here is our first tetrahedral intermediate in this reaction. So the carbonyl addition to the carbonyl happens, we produce a tetrahedral intermediate. Now this is a zwitterion. Now again, it's not an intramolecular proton transfer, okay? It is this multi-step transfer that I've been talking about. But for us, I'm gonna write in terms of the pedagogy of the class. When you're writing this out, please write it out fully, for instance, on the exam so that I can see that you know it. But we're going to say minus H plus to lose it from here, and plus H plus to add it to the alkoxide over here. And then that would interconvert our intermediate. And we have now a new tetrahedral intermediate that's neutral. Okay, now, normally, hydroxide is not a good leaving group, but remember our conditions, right? We're under 6 molar potassium hydroxide. And this is a really good nucleophile, a really strongly donating electron pair. Remember that alpha effect is still in effect. And so we can push out that hydroxide, again in a reversible fashion. Makes the hydrazinium ion and hydroxide. Okay, so we can, of course, with base, we're under strongly basic conditions. We will pluck off that proton, and this gives us we now have the hydrazone. Now, what happens next in these systems? And again, remember, here's our fundamental reaction. That we're trying to imitate. Let's just take this as acetone. So again, for simplicity in the mechanism. Okay, now, remember, these things are all reversible. We're going to find some irreversible steps, so keep paying attention. Let me redraw this here just a moment, because I want to look at this. So we have strongly basic hydroxide. And in equilibrium, now it might not be strongly favored, but we can pluck off a proton. We would have produced water. Of course, the counterion here, this was KOH. So we have the potassium here. Now, you've got to remember resonance and all of those things. Here, our lone pair can come down. Now, nitrogen can't have more than 8 electrons, so that pi bond has to swing over and be on the carbon. Now, what I'm drawing is a resonance form. Let's look at it. Now, putting in the lone pairs to help you see, the negative charge went from nitrogen to carbon. Now, this is just an allylic anion resonance form, but it's a hetero allele anion because we have nitrogens instead of just carbons. If we look at this resonance form, the carbon anion is a strong base, okay? And we're in water. Remember those pKa's for alcohols, a chapter or two back. This will deprotonate water, and this step is irreversible. Okay, it's an irreversible step. And I'm going to show that hydrogen explicitly. Once we make that strong carbon-hydrogen bond, KOH now won't deprotonate that, not carbon. But it's still, again, we're really strongly basic. We've got 6 molar hydroxide in there. We can pluck a proton off of that nitrogen. Now, I'm going to look at this with you briefly here. I'm going to draw that as a one-way arrow because I'm going to show you the intermediate, but almost certainly it doesn't really have significant existence. Okay, so we've deprotonated it. Of course, we lose water here when we do that. So let's look at it here. What do you see? Well, hopefully you see there is dinitrogen. So if that lone pair comes down here, and that's going to make a bond between these two nitrogens. Nitrogen has to lose an atom. Now this is almost certainly sort of a simultaneous reaction, but I'm breaking it down pedagogically so you can see it. Again, loss of N2 will be irreversible. That's nitrogen gas. Everybody take a big deep breath. Right, 78% of that's nitrogen. It's a very stable compound. That's fortunate because we wouldn't want our atmosphere to spontaneously combust and all life would end if that happened. Of course, there's hydrogen and the negative charge. Again, this is irreversible. Of course, in an aqueous environment, this will be a very strong base. It's a carbon anion. Methane's pKa is around 60. So this is a very strong base. And now we have replaced those the carbonyl, oxygen, around here with a CH2. That's what I call a mechanism-based reduction. So It doesn't involve hydrogen gas. It doesn't involve electron transfers. It doesn't involve metal hydrides or aluminohydrides or borohydrides or anything like that that would also reduce the nitro group. So you see, based on this mechanism, there's no reactivity of the nitro group, and that's how we achieve selectivity in our reduction. So chemists are often faced with these challenges of selectivity, and so we develop many, many different methods to be able to apply them in different situations and different scenarios to get high yields of useful products.